Okay, another common type of polar graphs or polar curves are circles. So when you see something like just a number times cosine theta or just a number times sine theta, then that is a circle. The a value is going to be the diameter. And then if it's cosine theta, the circle is gonna lay on the horizontal axis, like so. Okay, so 4 is the diameter, and we're gonna lay horizontally. So let's just make a little table. So r and theta, I always do my quadrant angles unless I have a multiplier in front of theta. Okay. So when I plug in 0, I get 4, then 0, then -4, then 0. So at 0, okay, at 0, I'm going to go out 1, 2, 3, 4. At pi over 2, my angle is 0. At pi, I'm back to 4 because it's negative. Okay, so I just have a circle that looks like this, and that's it. The next one, if I have a sine theta, a is going to be the diameter. So it's all in the way these equations look. Okay, if I have sine theta, the circle lays on the vertical axis. Okay, so my diameter is equal to 4, and then I'm going to be like r and theta. I have 0, pi over 2, pi, 3 pi over 2. At 0, my radius would be 0. If I plug in pi over 2, that's 1 times 4 is 4. At pi, I'm back to 0. This sign of 3 pi over 2 is -1, so -4. Okay. So at 0, I am 0. At pi over 2, I go up 1, 2, 3, 4. At pi, I am back to 0. At 3 pi over 2, I'm going -4, so I'm back at this point. So I have a circle that looks like this. Okay, so it just starts repeating itself after pi units. Okay, I have the next type of curve we have is a rose curve. These are fun. So if we have a multiplier times cosine theta, just kind of like a circle, but this time we have n theta. So remember, that's our angular speed. So that affects how fast we complete a cycle. So if the n is odd, then actually this should be not 2n, but n will equal the number of petals. Okay. And so if the n is odd, it's the exact number of petals, and a is the length of the petals. Okay. Let's just keep going here. If n is even, then we're going to have the number of petals is equal to 2n, so it doubles. Okay. And a is the length of the petals. Okay, at its like furthest point, yeah. If I have r is equal to a sine times n theta, then n, and n is odd, then n is equal to the exact number of petals, and then a is equal to the length of the petals. And then if the n is even, then the petals get doubled, so 2n is equal to the number of petals, and then this is still the length. length of petals. Okay, so for 4 cosine theta, 3 theta, we have an odd number here. So that means that the n is, if the multiplier is odd, you get that exact number of petals. So I have 3 petals, and A is equal to 4, which is the length of the petals. Okay, so we do have to figure out where did the petals start from. So we're gonna, and this is very important, the start. So for cosine, it's a little bit easier because when theta is equal to 0, the petals are at the furthest length, right? So when cosine of 3 times 0 is equal to the cosine of 0. So, and that is 1. So that means that the petal is going to start from the furthest length, okay? The other thing I need to figure out is how often each one of these petals occurs. So what we do is we take our 2 pi and we divide it by n, the number of petals there are. So 2 pi over 3 is how often the petals occur. So I'm going to go ahead and graph this over here. So the length of the petal is 4, and I know that at 0, the petal is going to start from its furthest point, because at 0, cosine is equal to 1. So if I plug it in, r is equal to 4 times cosine of 0, we get 1 times 4, which is 4. So I'm going to go out 1, 2, 3, 4. That's where the petal starts from. Okay. And then every pi over 2, every 2 pi over 3, every 2 pi over 3, a new rose petal is going to occur. So I'm going to go ahead from 0 to 2 pi, that's 2 pi over 3, and then we're going to have at 4 pi over 3, 4 pi over 3, another rose petal is going to occur. So 1, 2, 3, 4. Polars are nice because you get to count out on the diagonals as long as you imagine the little circles. Okay. It looks something like that. Polar curve. All right, next, 3 times cosine of 2 theta. So my A is equal to 3, and my N is equal to 2. So that's even. So I actually have to double that for the number of petals. So I have 2 times 2 is equal to 4 petals. Okay. Cosine, like I said, always starts at the longest part of the petal, always starts at 0. So I'm going to go ahead and cosine thetas start at theta equals 0. Okay, so I'm going to go ahead and start counting. My length of my petal is 3, so 1, 2, 3. That is my first petal. Now, how often do I have to draw a petal? Well, I'm going to take 2 pi over, and this time I have 4 petals, so that gives me pi over 2. So at every pi over 2, there's another petal. Okay, so that would be at pi over 2, at pi, and 3 pi. And I'm going to go out 1, 2, 3, 1, 2, 3, 1, 2, 3. So I go loop that, and like that. All right, now sine graphs. Sine is a little tricky because the petal does not start on the zero axis, okay, or the line 0. So I'm going to look at where does the length of the petal is 2, okay, and then I have an odd n, so the number of petals is 3, so that's 3 petals. Okay. This time I have to look at where this is going. What I do for sine graphs is I'm going to take my 3 theta, okay, or my n theta. So I'm going to take 3 theta, and I'm going to divide it by n, just like we did before, divided by 3, okay, and this time I get, oh, sorry, I forgot something. Okay, so I need to think about where is sine 3 theta, where is sine theta the greatest? Where is sine theta the max? Okay, so that's when sine is equal to 1. So when is sine equal to 1? Oh, at pi over 2. So that's normally where my petal is going to be, but we're off where the end of my petal is going to be, but we're off because of the multiplier. So we're going to take pi over 2, okay, my highest point, and we're going to divide it by our n. Okay, so take this away. I'm going to take pi over 2. That's my normal max. And I'm going to set that equal to 3 theta. And so what makes me do is divide by my n. And I get theta is equal to pi over 6. Okay. So at every so I'm going to start at pi over 6. This is my start. Okay, so you always take pi over 2 and you set it equal to n theta. So pi over 6. Wait. Okay, so this is pi over 6, I believe. Yeah, okay, pi over 6. That's where we're going to start from. And then how often do these petals occur? So how often is the same as before. We're going to take 2 pi, and we're going to divide it by n, which is 2 pi over 3. So every 120 degrees. So I'm going to have to add from pi over 6, I'm going to have to add 2 pi over 3, which is times 2, so 5 pi over 6. So that's right here. 5 pi over 6. And then I'm going to add one more, so 5 pi over 6 plus 2 pi over 3 is equal to, say I'm adding 4, so 9 pi over 6, which equals 3 pi over 2. So straight down there. That's how often these petals occur. So graphing. Radius is 2 at each one of these junctures. And I'm going to start by going this. Petal, petal, petal. Okay, last one. So r is equal to 3 sine 2 theta. The a is equal to 3. That's the radius. The n is equal to 2, so that's even. So I have to do 2n is equal to 4 petals. My start, I'm going to take pi over 2, and I'm going to set that equal to my 2 theta. Okay, and so now we're going to divide to give me pi over 4. So I'm going to start my graph at pi over 4. Now, how often is I got to take my 2 pi and split it evenly by the number of petals, so by 4. So every pi over 2 radians. So pi over 2 would just be 90 degrees. So at, 3 pi over 4, 5 pi over 4, and 7 pi over 4, and then we go back. That splits that up evenly, yes. Okay. All right, graphing time. Radius of 3. 1, 2, 3. 2, 3. 1, 2, 1, 2. All right, and that's what we got. The last type of curve we're going to go over super quick here. It's when we have it's called a lemniscate. I think it sounds like lemon biscuit. And it looks like the equation like r squared is equal to a squared times cosine 2 theta or sine 2 theta. The a value is equal to the length of the curve. Okay, and then we have to do a little bit of trickery like we did with the rose petals to figure out where they start from. Okay. So 9 is equal to a squared, so a is equal to 3. Okay, and if we think about the cosine of theta, then it has its longest point when cosine theta is equal to, so we're going to say, when is cosine of what is equal to 1? That's when it's equal to 0. So we want to figure out when 2 theta is equal to 0. So what theta do I need to plug in to give me a 0? Well, theta is still going to equal 0. Okay, so we're going to have the longest point at 0. You guys can make a table if you want, but a lemniscate only has 2 parts to it. So what it is at 0 here, we're going to go 1, 2, 3 units. And then at, let's take our 2 pi and divide it by 2. Okay, since that's our n value. And I get pi. So at pi, 1, 2, this is like a 2. This is like a 2-petaled rose, kind of. Okay, so what this is it starts here and makes a kind of infinity sign. Okay, all right, the next one. So my a is equal to 3, and then this time we need to figure out where sine starts from. So I know the highest value of sine is at pi over 2. So I'm going to set that equal to my 2 theta, divide by 2. Theta is equal to pi over 4. So at pi over 4, I'm going to have a point at 3. And then, so this is the start. And then how often, we're going to take our 2 pi and divide it by the n, which is 2. So at every pi. So just directly across, I think that's directly across, I'm going to have another petal here. Okay. And that is a lemniscate. Those are our common curves. So limestons, lemniscates, and roses and circles are really our common curves. Okay, cool.